Okay, welcome back to class, everybody. It's a good time to get started, and let's just begin by briefly reviewing what we talked about last time. So we began class with any questions that you might have on homework 6 or anything else. And then we spent the majority of class talking about collecting data from the web. And in particular, we saw a tool called Scrapey that allowed us to write relatively little code and do very complicated data collection online, okay? So I hope that that's something that you find useful. And then towards the end of class, we saw some options that you have for making your Python code fast. By far, the one that's easiest to use is the vectorization that we did earlier in class, because it's easy to install. All you need is SciPy, and it works reasonably well. But if that's not enough for your application, if you're worried about making it even faster, you can invest the time to do things like write custom C code or install Numba on your computer, and then you can get significant improvement. So maybe on the order of 5 or 10 times faster code by doing those things. So the plan for today is the following. I'd like to just begin with any questions that you might have on homework 6 or your projects which are coming up or the exam or anything like that. Then one of your classmates asked me to do a practice exam in class so that you have an idea of what exam 2 is going to be like. So we're going to do a practice exam in class so that you know exactly what the exam is going to look like, okay? And then, depending on the amount of time that we have, we're going to talk about SQL and Python. So the primary way that we learned in class to deal with data is pandas. And pandas is going to be great for you probably 95% of the time, maybe 98% of the time. But sometimes you have very large and complex data sets, maybe on the order of gigabytes that don't fit in memory, that really need to go into disk. And that's why people have developed database software like Postgres, MySQL, SQLite, Oracle, and so forth. And Python has some really nice tools to interact with those databases. And so depending on our time, we'll take a look at SQL Alchemy, which is, I'd say, the primary professional grade tool for doing SQL and Python. And I've used it for research many times before. It's incredibly useful. It makes otherwise very, very difficult things both fast and easy to write. Okay, so let's just get started with any questions that you might have on homework assignment or projects or upcoming exam. Yeah?
How long is the second exam, just 1 hour?
No, it's going to be exactly the same as the first one. So that means the actual description and data is going to go up right around 3:30, and then you're going to have until 5:30. Okay? So one comment, which is last time a few of you said, oh, you know, like I turned it in just a couple of minutes after 5:30 and the submit link went away. The same thing is going to happen. Like at 5:30, that submit link is going to be gone. Okay? So that means like you just have to turn it in by 5:30. That's the way that it works. So other questions about exam or homework assignments or projects? Okay, if not, let's just get into taking a look at what the exam is going to look like. So as I've said multiple times in class before, this exam is really going to be about implementing an integer program. And so this is an example kind of write-up that you might get on the exam when it becomes available at 3:30 next Tuesday. So in this exam, you will implement a mixed integer program to solve the elementary shortest path problem with resource constraints. So, you know, this problem should ring a bell for you, but like the one that you get for the exam may not. Okay, so it may be a problem that you haven't seen before. But this is the problem that you're solving on homework 6. Okay? So you're already a little familiar with this problem because you have to code a special purpose optimization algorithm for your final homework assignment. Okay, so the mixed integer linear program can be described as follows. You're given the following data. So this is exactly how the exam is going to look. So you're going to get a description of what the integer program is. So let's read this description. So we get a set of nodes, a set of directed arcs, a set of resources. In our case, these are just time and volume. A start node, for us this is a node called start. An end node, for us this is a node called end. The cost for each edge, the resource usage for resource R on edge UV, a lower limit for resource R at node U, an upper limit for resource R at node U, and a big number, and for us this is going to be 1,000. Okay, so you're going to get a description that looks very similar to that. And then the MILP has two groups of variables. XUV is a binary variable specifying if we use edge UV in the shortest path, and TUR is a continuous variable specifying the resource usage for resource R at node U. Okay. And then you're going to get, in symbols, the description of what the mixed integer program is, right? So objective function, a bunch of constraints, and also something telling you about the variable. So in this particular case, the x's are binary and the y's are, or the t's are going to be continuous. So download the file data exam2 data. It contains two data files, arcs and nodes, that have the relevant data for the above problem. Use these files to create the MILP and solve it. In the end, read the solution variables and print out solution to the screen with statements similar to this. Okay, so the task list is going to be exactly the same. You get a MIP, you get a bunch of data files, and what you have to do is program how to solve it and then print out the actual solution at the end. Okay, and then to debug, try deleting the time limit upper bound on the node end, or setting the time limit upper bound on the node end to 100 and resolving this problem. Okay, so then once you go and download exam2 data, you're going to get data files that look like nodes. Okay, so here for each node, we get the node name, the upper and lower bound on the time resource constraint, and the upper and lower bound on the volume resource constraint. Yeah?
In the exam also, data will be like very small, or so that we can check, verify it?
It's going to be something that you should be able to solve in your head. And similar to this problem, the actual answer is going to be in the write-up. So this is actually the answer for running that MILP on the data that I've provided. So you should be able to check if your answer is correct in multiple ways. Okay. So let's take a look also at the arcs. Okay, so for the arcs, we have a start node and an end node, a cost on the arc, time resource usage, and a volume resource usage. Okay, so those are all the things that were needed to specify that problem. Okay, so now our task is to write some Python code to solve this problem. So to do that, I'm just going to put this on the side here so that we can maybe be looking at the MILP formulation at the same time as we're coding so that we don't have to constantly flip back and forth. Okay. One second. Okay, so help me write this. So I'm just going to start us off in the usual thing that we do. So I need to read in the data files, right? So I'm going to import pandas. And then from Piomo, we usually import these things. So Piomo environ as PE and Piomo.opt, because we need to create a solver with Piomo.opt, okay? So here I need to just read in the nodes data and arcs data, or let's just call it node data and arc data. Okay, so, and I always like to test my code as I'm writing it, so let's test it here. So we're going to run the solution. And here we have some node data and some arc data. Okay, so what should I do next? Right, so I need to start creating the Piomo model for this. To do that, I need to define the sets. So create the Piomo model. So M is going to be a concrete model.
When do you not use a concrete?
So really for us, we're only going to use a concrete model. So the reason that an abstract model exists is because the Piomo developers have built in some various tools that let you abstract the model right up from the data. So they let you have like a data file that's a separate file from the Piomo code, and then you can create an abstract model and call it with particular data. But for us, the reason we always use a concrete model is because the way that we're getting our data is always with pandas, always inside the program itself, and not with something that Piomo has built for us. Okay, so what are the sets that I need to define?
Nodes.
Yeah, nodes and arcs, right? So let's compute them here. So the node set is going to come from node data.
Here's a question that right off the bat. A lot of times when you do this, you say node set and then you just take like the data frame or initialize it or whatever. But you're not actually making it a set, like a PE dot set.
What do you mean?
Or are you? Like a set, like a parameter, like a variable.
Oh, but sometimes I call unique to make sure that that everything appears only once.
I'm more talking about the Python or the Piomo environment, like saying a set. I'm using the terminology.
Yeah, so usually we do something like m.nodeset equals PE set.
Okay.
So we're definitely going to do that.
Okay.
And that's something that we have to do because we're going to define constraints over that set, variables over that set, and so forth. Okay, so first we have to compute what the node set is. And the way that we've done that before, and let's kind of do it similarly here, is, or I think it was maybe set index on node in place. So hopefully this computed the node set. Let's run it and see what happens. Yeah, so the node set is start, A, B, and end. So let's do the same thing for the arc set. Except for the arcs, we're going to index on start node and end node. So hopefully all of this is looking familiar, right? No surprises here. Okay, so those are the arcs that we read in. And sometimes I like to have these sorted so that just printouts look nicer. So maybe I'll sort them. Okay. Okay, so I computed what the sets are, and now I have to actually create the Piomo set. So here's when where I actually do m node set equals pe set initialize with a node set. And the arc set, I'm going to initialize with the arc set, and its dimension is going to be 2. So again, no surprises here. And you know, I like to check that the code I've written so far works okay. So here we've defined 2 sets on the model. Okay, so some other things that are going to be useful for us, just kind of looking through here, is we're going to need to do things like find the successors and predecessors of a node for these sums. Okay, we've done that before. And let's maybe, I was going to suggest like making a dictionary of predecessors and successors that maps a node name to the set of predecessors and a node name to the set of successors, right? So let's maybe do it right here. So preds is going to be a dictionary, and then for node in node set. Predecessors for this node is going to be equal to arc data, where arc data dot n node has to be n, and I want to look at the start node for that. Does that make sense? And then similar thing for the successors. So now if I run my code and I look at preds, so the predecessors of A are going to be 0 start, 2, and B. Or let's just look at preds A. And let's take a look at arc data. So the predecessors of A should be just start and B, and A is just start and B. Okay, so looking pretty good. Okay, so now help me write the rest of it. So what do I need to do next? Yeah, create the variables. So we're going to have 2 variables. So we're going to have x's. That's is going to be a variable. And how many x's are there, or what are they indexed by? So x is a binary variable specifying if we use edge ij in the shortest path. Yeah, so that's right. So x's are going to be indexed by the arc set. And then we're also going to have these t's. So it's a continuous variable specifying the resource usage for resource R at node U. Okay, so what about the t's? Over what set do I define? That's right. So I need to define a resource set. So it's a set that we forgot to define. So let's call it resource set. And what are the resources in this particular example? Yeah, time and volume. So maybe we hard code those like this. Okay. Another option for this, instead of hard coding it, is you could have computed it by looking at the column names of the node data or the arc data, right? Because they're in there. Okay. So here, yeah, so over what do I define the t's? Yeah, resource set, not arc set. So T is a continuous variable specifying the resource usage for resource R at node U. Yeah, times m dot node set. Okay. It's creating a T variable for every combination of resource and node. So this means cross product, right? So it's creating a T for every resource comma node. That's right. That's right. And let's run it and actually see that that's what's happening. So if we look at m.t, we have a T for time A, a T for time B, a T for time end, a T for time start, and then we have the same for volume. Make sense?
The dimension is the indices, right? So if you said dimension equals 2, that's saying we have 2 indices.
Yeah.
Starting and ending.
That's right. But dimension equals 2 only happens on sets.
Right.
And variables you just define over sets, right? Okay. So I've created the variable, so now what do I do? Yeah, I have to write the objective and I have to write the constraints, right? So let's do that. So create the objective. So let's define the objective rule. It's going to take a model in it. And what is it going to return? Yeah, so how do I get the C's? So the C's is the cost on each arc. And I have my arc data here. So I can do something like arc data index for edge E cost times m x for that same edge for E and m dot edge set. And then I could do m dot objective equals p objective with this rule, and the sense is p dot minimize. Does that look familiar? Okay, so let's run it and see that we've done things correctly. Okay, so there's no edge set, and I didn't mean edge set, I meant arc set. So let's rerun it. And now if I look at the objective, I'm getting just those negative costs times each of the x's, right? And that's because if I look at my arc data, the cost column is -1 for each one of the arcs. So that's why I have just a coefficient of -1 in front of all the x's. Make sense? Okay, so now let's create the constraints. Okay, so these first 3 constraints look really, really similar, right? And in fact, they should look pretty familiar to you. What do they look like? Yeah, they look like the shortest path, like imbalanced network flow type stuff, right? So this is exactly the same. The only thing that's changing is the right-hand side. So let's write it the same way that we've done it before for shortest path. So instead of writing 3 different constraints, I'm just going to write one constraint with an if statement inside of it that changes the right-hand side, okay? So let's call it Netflow Rule. And it's going to take in a model M, but what else does it take in? Yeah, a node U, right? Okay, so the first thing I need to do is figure out maybe what the right-hand side is. So let's say the right-hand side by default is 0, and if U is S, which is this one, the right-hand side has to be 1, right? So for us, S is going to be the node called start, and T is going to be the node called end, okay? So how do I write an if statement that checks if U is S? Oh, so U actually, it has a name, right? Like its name is start. So I could just directly do something like equals equals start, then right hand side is -1, right? Because that's the actual node name is getting passed into this constraint. It's not sort of where in the set it is. And if U is end, then the right hand side is going to be 1, right? So now I've computed what the right hand side should be. And there's lots and lots of other ways to do this, but we chose to do it this way right now. So what do I return? So the sum of the x's, right? So I need to, so the x for a particular, let's say, AU for A in what? Yeah, and we computed a set of predecessors earlier, so here I'm just using that, okay? And then I have to subtract from that the sum over m dot x UA for A in what? Yeah, the successors of U. And this difference has to equal the right-hand side that we computed. And so m dot netflow constraint is going to be p dot constraint. And what do I pass into this constraint? Like m dot node set, and then the rule, that's the network flow rule. So why do I pass in m dot node set here? Yeah, because I need to create one of these constraints for every node. So let's run it. So error accessing index component A start is not a valid for array component X. So let's see where that is. So it's in one of my sums. Say again? Yeah, so I think that the error is probably in our predecessor. So let's look at predecessor start or something like that, or predecessors A. So the issue is that it's a data frame, right? But I really want it to be a list. So let's go back up there and change it to a list. So here it's a data frame, but I really want just the values of that. And I think this should change it into a list.
You could as well just convert the data frame like index also, right?
So the index is actually just going to be 0.
Yeah, so if we re-index it to the names of tools, that could work.
Yeah, so there's other ways to do it for sure. Okay, so I'm getting my error again. So let's see what that is. So it looks like we're trying to index A start, right? So let's see if what the successors of A are. So the successors of A says start B, which means I didn't compute successors properly, and that's because I want the start node to be N, and then I want to look at the N node, right? Okay, so now things are looking okay, and then we can look at the network flow constraint and then pretty print that. So by the way, definitely very common for me to like have errors like this in my code as I'm writing, right? So I expect you probably have to do a little bit of debugging as you're creating your code, same as we're doing right now. Okay, but this is looking pretty reasonable, right? So it's a bunch of x's minus a bunch of x's. So if we look at A, there's a incoming edge from start and from B, outgoing edge to B and to end, and it has to equal 0. And if we look at start, there's only an outgoing edge start to A, and it has to equal -1. Okay, so things are okay. So help me write the next constraint. So let's call this the resource constraint, the resource rule. And so it's going to take a model for sure. And what else does it take? That's right. So it takes actually three things. It takes a resource. Let's call that R. It takes also a node U and a node V that's going to come from an arc, right? So let's write this. So what do I return?
So if we take U and V, we'll have to check if U and V are in an arc. If we just
I'll show you how we make sure that they're in arcs in just a moment, and it really just has to do with what we pass into P constraint, right? Because that. Say again. Oh, that's what we're going to do. We're going to pass in only arcs to this function. But help me actually write out what the return value is here. So how do I refer to this, right? Like this, I have to write the left-hand side less than or equal to this right-hand side, right? Yeah. So, yeah, m dot t. And what was t indexed by? Let's go back and check. So t was indexed by a resource and a node, right? Okay, so m dot t, and then what do I pass into it? R comma u. How do I know that? It's R and U, okay. Then what do I need to do? I need to add to that. M dot t is a variable. It's the yeah, so it's the continuous variable specifying the resource usage for resource R at node U. Okay. In the code. Well, but this brings up a good point, which is I forgot what the domain of this should be. What should it be? Right. Because they're going to be 0, 1s. Like, do we use that class or use that edge or not? Okay, so we're still trying to write this.
So can you go to the definition of like where it's
So where's the D? Is the D?
Yeah, what does D mean? Let's go back and look. So D is the resource usage for resource R on edge UV. How do I get at that?
Well, I don't remember where we. Is that an attribute? Is that an attribute of data that's on the node already?
Well, where would it be?
I mean the edge of the.
So it's certainly not a variable, so it's a piece of data, right? And it's going to be on the arcs because why?
I guess we assigned it as an edge attribute.
Well, it's the resource usage for an edge, so it has to be on an arc, one. Another way that you know it's on an arc is the fact that it has a UV on it. Okay, so how do I get at that in the code here? Yep. Arc data. Yeah, which resource is it? It's resource R. Yeah, it's like whatever got passed into this function. Okay. So I need to index this with UV. So I'm looking for that edge, and I'm looking for that resource. Does that make sense? So why this? Because my index was an edge. So here I've created the edge. So I'm going to index that into the arc data frame. And which column do I want? I want the column that's specified by R, right?
R will either be time or volume, which is your column.
That's right. And how do we know that it's going to be either time or volume? It's because we initialize the resource set to be time and volume. Okay. So help me continue writing this. So I have this T, I have this D, and then so minus T RV, plus, for us, M was 1,000, so that was written just at the beginning of the document here. So a big number for us, this is 1,000.
If we change this, so probably should declare it at the beginning.
Yeah, we could do that, but
We have to change it later.
no, we're not going to have to change M. We're going to have to change some of the data. Yeah, M dot X at UV, and that has to be equal, or that has to be less than or equal to 1,000, right? But, another way to do it is right up here where we're reading in our data. We can say M equals 1,000. And then here we could just say M. So let's do this resource constraint is equal to P dot constraint. Okay, so tell me what to pass into P dot constraint. So the rule is clear, so that's going to be this resource rule that we just wrote. But over what set do I make this?
The resource set and also the arc set.
Yeah, so certainly the resource set. So how do I say the resource set and the arc set? Right, because I want the cross product of those things. I want every combination of resource and arc. Does that make sense? So this is exactly the same way that we define the T variables, because we needed a T variable for every combination of resource and node. So let's run this and see if it looks right. So we called this resource constraint, so let's print it. And for the last one, so this is the resource for volume and the arc start A, and it looks like 2, which should be the data usage of, or the volume usage on that arc of T volume start minus T volume A plus 1,000 times X star A is going to be less than or equal to 1,000. And just to make sure that we're doing the data properly, we could look at arc data. And the volume usage for start A is 2. So that matches up with that 2. So it looks like we're doing this reasonably.
Is that 2 the D?
Yeah, 2 is the D, exactly. And it matches up with our code right there. So that's where we are accessing the D in the write-up. Okay. So almost done. We only have a couple of things to do, which is this resource usage lower bound and resource usage upper bound. Okay. So help me write those. So let's call it resource lower bound rule. So what is that going to take? It takes in a model and what else?
Is there no way of doing an implicit bound?
There is when you define the variables, but let's do it this way. Let's write a constraint. So what do I pass in? Yeah, resource in the node. So let's call it R and U. And what do I return? So where do I get the resource lower bound and the resource upper bound? Yeah, the node data. So let's take a look at it. So it's time lower bound and time upper bound. So I need to return, since this is the lower bound, I need to do something like node data indexed at this node like whatever resource it is, lower bound. Yeah, absolutely. R plus LB, right? Because it's the resource name plus lower bound to get the lower bound, and the resource name plus upper bound to get the upper bound. And that has to be less than or equal to what? Yep. And so let's do m dot resource lower bound constraint is going to be p constraint. And what do I pass in here? So resource set times m dot node set. Okay, so why didn't I do it the other way around? Why didn't I do node set times resource set? Yeah, so what I pass in here has to match in order with what I am taking in there, right? So if here I did like node and then resource, then here I would have to do node set and resource set. Make sense? And then the rule is going to be this resource lower bound rule. And let's run things to see that it's doing okay. So, so constraint, this does not have a proper value found true. So let's see why that would be. So for volume A, and that's because the node, when we define this these t's, by default they're non-negative reals, okay? And what we're saying is 0 has to be less than or equal to a non-negative real number, which is always going to be true, okay? So let's fix that error by saying if the lower bound is 0, skip this constraint, okay? So this is the lower bound. And here I want to say if lower bound is 0, do you remember how to say to skip this constraint? That's right. So here we're going to check if the lower bound is 0. If it is, we're going to skip it. Otherwise, we're going to add the lower bound constraint. Okay, so let's run things again and see if we get the same error. So time A does not have a proper value found true. So let's see. There's another way for us to debug things, which is to actually call that function directly to see what's happening when we're executing it. So here we can pass in the model and time and A. So error evaluating expression, no value found for initialize something, something. Okay. Let's just print the lower bound here and just cause an error. I'm thinking that perhaps I'm not taking the lower bound out of the problem correctly. So So let me just try node data index at A time plus LB. If the lower bound is 0, we return constraint.skip, otherwise that. All right. So other ways to debug is to just run the debugger. So let's try to do that. Yeah. Time LB and volume LB and upper bound. So I checked. I'm getting the time lower bound correctly, right? So let's just try to do this, like 2 less than or equal to m dot t for time and A. So that seems to be working okay. So, say again? Yeah, so I tried that a little bit ago. So this was me trying that, right? So passing in a node, the resource name, which would be time, and then plus LB, and that returned the 2. Okay, so I want to try calling it again. So first should be the time, and then the node. Oh, and then I need to pass in the model as well. And that returns true. But if we do 2 less than or equal to m dot t of time in A, that actually returns an equality expression. So let's try to do this. I'm just going to print this and then maybe return, let's just hard code returning 2 less than or equal to m dot t of RU. And just to double make sure, when we defined our times, yeah, it's resource and then node. So I'm not messing that up. So constraint time B found a double-sided inequality expression, lower equals an expression, but the upper bound was non-constant. So the other thing that might be going on is maybe we have some sort of something kind of lying around in the interpreter namespace. So just restarting the interpreter. So the other thing that I think might be is that typically when we define constraints, we have an expression on one side and maybe another expression on the other side. So I'm thinking that maybe the issue is that this isn't an expression. So say again? N dot T of time in A. What are you saying is a set? And if I do the negative of that as Pratik suggests, then it's it's an expression. So let's try to do what Pratik suggested. And we could say that the negative of that is bigger than or equal to the negative of the lower bound. Say again?
Probably switch the order.
Switch the order of...
And we should come to the right hand.
You wanted to do what?
Swing M on the left and LB to the right.
Why do you want to do that? Okay, so other things we could do to debug is try to do the built-in Piomo lower bounds and upper bounds on variables. So let's sort of take a look at that. So Piomo documentation. Okay, so it looks like we can pass in some bounds, but it doesn't exactly say. So bounds, a function or a Python object that gives a lower upper bound pair for the variable. Okay. So what we could do perhaps is something like this. So it's going to take in a variable, right? So it's going to be a resource and a node. And it's going to return a lower bound, which is going to be node data dot index this node, this resource plus lower bound. And then the same thing plus upper bound for the upper bound. And then we could try something like bounds equals T bounds.
I got it to work if you just put them both on one side. Less than equals 0.
Yeah. So, okay, so you want to do like LB minus M.
Yeah, I saw your T-bounds doesn't have the arguments in there.
Let's say again?
When you up there, bounds equals to,
Yeah.
is that not? Oh, no, that's a rule. I don't know.
So T-bounds takes exactly 2 arguments, but 3 are given. So let's rerun it. So let's do, let's first pretty print T to see if we use bounds correctly. So now time.a has a lower bound of 2 and an upper bound of 4. And if I look at node data for A, the time lower bound is 2 and the upper bound is 4. So it looks like we used bounds correctly. Okay. So how did that work again? was we defined a function that looks very much like a rule. It takes in the model and variable index, and then returns a pair that's the lower bound and the upper bound for that variable, okay? And maybe this is even easier than defining the individual constraints. But when I ran it, also the individual constraints look like they worked. So let's take a look at that, which was the resource lower bound constraint. And now it's sort of giving us the expressions that we were expecting previously with the various skips and so forth, okay? So this really does have to do with the fact that when you pass in a single variable, Piomo doesn't treat it as an expression, it's a variable. So probably when we're doing variable less than or equal to constant, it's doing something that we don't quite expect. Whereas the reason we haven't run into this problem previously is because we're always adding a couple of variables or doing some sum over variables for that expression. So since our bounds worked okay, let me just kind of get rid of those constraints, those lower and upper bound constraints, and run it as we have it. Okay, so that defined these lower and upper bound constraints, and now I can actually try to solve it. So and really, I often forget how exactly the solver lines go. So what I would do, and I think it's a perfectly reasonable thing to do also as you're taking the exam, is just look at one of the other examples we did in class. So let's just take a look at the facility location one. So this.
Also, online where you have facility location, it just pulls up the...
I think I fixed that. Somebody sent me an email about that. But yeah, thanks for letting me know about that. Okay, so here are two solver lines. So we create a solver and then call it on the model. So I'm just going to cut paste these into our file. So that's just a problem with cut pasting. Okay, so let's rerun everything. And what we really want is the x's, right? So let's take a look at the x's. It looks like the path is going from start to A and then from A to end. And in the solution that is in the document, it should go from start to A and from A to end. And so it looks like our model is working, at least on this small example data set, is producing the answer that we actually wanted to produce. But of course, we wouldn't be done if we're doing the exam, because we actually have to print that out. So help me print out the path that we have to take. So we have to do something like current node is going to be start. So that's going to be the beginning. The path is going to be maybe empty at the beginning. And we're going to do something like while current node is not equal to end, path.append the current node. Say again? Oh, yep. So we append the current node to the path, and then I need to iterate over all the successors of the current node. So for n in successors of the current node, I need to see if m.x of the current nodes to n, if that value is bigger than, let's say, 0.99. So if it is bigger than 0.99, I've identified where the path is going next. And so the current node is going to be equal to n. And then I can break because I've identified where it's going next. And at the end, maybe we can print the path is path. So let's run that and see what happens. So the path is start to A. And it looks like my loop here doesn't append current node. So maybe I should do that and that. And then if I rerun it, then the path is start to A to end. And then one of the things that it told me to do is try debug by editing the time upper bound on node n to 100 and resolve the problem. So let's take a look at the values on our nodes data. So the node end, the time upper bound is 5. And if we open up the arcs, we're basically using 1 unit of time on each move, right? So start to A, the upper bound is going to be 1. A to B, the time usage is going to be 1, and so forth. Okay, so the idea here is let's just kind of think about what we should be getting instead of just kind of trying things out. So ideally, what do I want? So these are all the arcs, and I want the minimum cost path without repeating a node. So what would be kind of the ideal path if I didn't have node constraints or resource constraints on the nodes? Well, if I do start to end, the cost is just -1. But I want, I want start to A to B to end, because that's going to give me like the most negative cost, right? But right now, I'm not getting that. Right now, I'm just getting start to A to end, right? So why is that? So the A time lower bound and time upper bound is going to be 4. So I basically have to go to A before I go to B because of the time lower bound and upper bounds on B, right? And because n's time upper bound is 5, is it possible for me to go to B before going to end? No, right? But if I change n's time upper bound to 100, then I can actually do start to A to B to end, right? Okay, so let's change this to 100 and rerun. Okay, and then we get the path start to A to B to end, okay? So in a very similar way, the exam that you get is going to ask you to run one instance of the data and then a second instance of the data, okay? It's really useful to spend the time to kind of understand what the solutions you should be getting should be before you actually run it. And it's going to really help you debug and like understand your code. But at this point, we would be done, and we could do things like put a couple of comments in the code, which we actually did as we were coding, and your code should run and print the solution to the screen if I place the CSV files in the same directory. So that's how I'm going to be testing it, right? So I'm going to place the CSV files, potentially not the CSV files that you had on the exam, right? I could use totally different ones just to check that your program is running correctly with new CSV files, right? And it should print the solution to the screen. So makes sense, and any questions about the exam format or what to expect about it, on it? So do you feel reasonably confident doing this next Tuesday? I mean, we've done a bunch of examples on this, about things like this in class. This is probably our fourth one. And we've done like a large variety of them in terms of like road generation, facility location, shortest path, this one, and so forth. And it's definitely an important tool if you're going to do essentially any optimization problem for research or work after this class. So it's really worth being able to do this in a short amount of time.
Could you clarify when, I mean, the cross product thing, I'm not sure I naturally recall how to do that or when that's the right thing to do.
Oh, so when did we use cross products in this example? So we didn't use it on the x's. So why didn't we use cross product on the x's, even though it has two indices, a u and a v?
Those are related to the edges which already have them.
That's right. That's right. Edges already have dimension 2, right? They already have a u and v, so that's why I don't need it on the x's, because my arc set already has two things on it. So why did I use it on the t's? So when we defined the t's, I had
okay. So the resource usage was related to the arcs, but then you were multiplying it by the nodes, or no?
So I defined my node set, arc set, resource set, and when I define the t variables, here I'm using resource set times node set.
The consumption happens over the arcs, right? Being tracked.
That's right. That's right.
Okay.
So there's two questions. So one question is kind of semantically, why are the t variables indexed by these two things? Semantically, it's because we need to check that the resource usage at each node is within its bounds, right?
Okay. Yeah.
So in this problem, I have to check, like, hey, is this bigger than the lower bound or bigger than the upper bound,
okay.
right? So that's why semantically they have two indices. But just syntactically, why did I use a multiplication there for this thing? It's because it's for every pair of resource and node. And that's not some kind of set that we already have. It just means for every pair of resource and node. And so here, I actually have to do for every pair of resource and node. So other places where we used the multiplication was right here. So when we defined this constraint, which was our resource usage constraint. So let's kind of read it to understand it and then talk about, again, why we use the multiplication rule. So what is this saying? Take the resource usage at U. Add how much ever resource got used as I travel from U to V, okay? And this, like, if X is 1, it means I actually use that arc, right? If X is 1, the two M's on both sides are going to cancel, right? So if I use that arc, then this sum has to be less than or equal to how much resource I'm using at node V. Does that make sense? But if the X is 0, which means I'm not using that arc, it means that this constraint is vacuous, basically. Because the M is so big that the right-hand side is always going to be bigger than the left-hand side. So basically, we're using the M to turn that constraint on or off. If you use that arc, the constraint is on, and if you don't use the arc, the constraint is off. So that's what the constraint means. So why did I use the multiplication here of resource set times arc set? Right, so here we're using M resource set times M arc set. So why is that? Where does that appear on this write-up? Yeah, because I need to make one of these constraints for every resource in R and every edge in A. Okay, so that means for every pair of resource and edge. Make sense? Other questions? Okay, so we have only about 5 minutes left of lecture, and it's really not a sufficient amount of time to do a proper exploration of SQL and Python. So it's something that's incredibly useful. I'm going to post a video of it online so that you guys can just look at it and learn about it yourself by looking at that video. But in terms of lecture, this is kind of be the last lecture that we have for class, right? Because from here on, next Tuesday is the exam, and after that, I'm looking forward to hearing some excellent project presentations from you all for the rest of the semester. And over probably today or tomorrow, I'm going to send out the final project presentation schedule with presentation titles and so forth. So one last bit of administrative info on project presentations is I'm going to have each of you sort of write some reviews for at least 2 other randomly selected presentations. So I expect you all to be present and come and listen to these presentations for a number of reasons. So first, they're usually super interesting. I mean, people have done a lot of work on these things, and usually there's a lot to learn from them. And second, you know, you put a lot of work into yours. You want people to listen to you, so come and listen to the people who are talking, even though we're not going to obviously have an exam over them at the end of the class and so forth. Okay, so thank you very much for listening, and I'll see you all next week.